Okay, hello. This is Majid, and again, here I am with the team from Moorcheh AI, Tara, Het, Rasa, and Neil. And today we are talking about the work that Rasa has been focused on for a while, and that's looking at the benchmarks for AI memory. And just to give a bit of background, so we've been developing MUMLA, which stands for Moorcheh Universal Memory Layer for Agentic AI. And we have gone through how it works and its structure. It's going to be released soon. Uh, but behind the scenes, we've been studying deeply on how others are handling memory for AI. What are the challenges? What are the most difficult questions that an AI would have to answer? What are the time frames for a long conversation? And how is the best methods to retrieve them? And without further ado, I will ask Rasa to start talking about his findings. And also, he has put together an article, which is we'll be publishing it first as a blog post, but potentially could be a research paper, um, which talks about our findings about the memory, especially using MUMLA. Okay,
Yeah,
let's go on.
yeah. So I've been like doing a lot of research into like other agentic AIs. How exactly is like retrieval accuracy valued? Like how exactly do you measure how good a memory system is? And these are like very recent discoveries. And what I found is mainly that there are two benchmarks that are used to evaluate long conversations. So first is Locomo. So the Locomo dataset is a string of 10 different conversations. So 10 different conversations, and then you have a total of 1,500 or so questions to ask on these conversations. So the conversations are between two people. So these are sort of an example, like is a back and forth between two people, and then there are multiple sessions, and then it'll keep going on, and then the benchmark will ask you to answer questions on these. That's one of the benchmarks. And then a more recent benchmark, which is the Long-Mem benchmark, is sort of a longer session. So it's intended to test memory over a long period of time, because that's what you kind of want in a memory system, to be able to recall facts that you mentioned a long time ago, remember preferences, and like be a general assistant. So these are some of the
Yeah.
questions that they're trying to test. So mainly there are 7 categories. So you have general regular questions. They ask you questions about your preference. They also test more niche things, so such as knowledge update. They're testing that your memory layer or memory system can sort of take in a piece of information, and then
Mhm.
it'll receive new information. It can update on that information. And they also want to test other things such as,
Yeah, I would say abstention is an important one because they want to watch for hallucinations. If there's, if you ask something that's not really in the conversation, you want the agent to know that this was not part of our conversation and say that this is not, and prevent hallucination. Like watching for hallucination. Yeah, keep
yeah,
going. What are the other categories?
yeah, and some other more difficult categories like temporal reasoning.
Yeah,
So
and the
like this is an
single
example.
session assistant is just, which means that the answer to this question is within one session, right? Or
Yeah,
the AI could answer that. Okay,
yeah.
yeah.
And like temporal reasoning is more complicated. You can sort of see how the question is structured. If you want to figure out how many months have passed since my last visit museum with a friend,
Mhm.
this question was asked in June, and then it has to go back all these conversations and look back to a conversation that happened in July, and then it has to interpret that June is 5 months after January.
January, yeah.
Yeah, January. And then it says 5 months. So there are some complicated questions in here. And then there's like multi-session, which is like, how many musical instruments do I own?
Mhm,
And it has to search across a bunch of different sessions. So like conversations spanning like hundreds of
mhm,
back and forth between the user and the AI. And the goal is to find particular mentions of their when they use musical instruments,
yeah.
and then come up with an answer.
This is very interesting because this is like sophistication of a human memory. Let's say you have a friend, he mentions, oh, I bought a Fender guitar this time. And then you meet him like 3 months later, and he says, oh, I bought a piano. And that's it. And then so, somehow you know how many instruments he has. Not even a human is for a human it's difficult to recall all those things and add them all together and make conclusion. But this is the expectation from some of these questions. And now I want to ask you to put some numbers on stats on these. So how many questions and how many dialogues are within Locomo and Long-Mem?
Yeah, I mean, I can go into like the exact is a lot to scroll down if I actually go
Okay.
into them. But to give an idea, the file is like 300 megabytes, and it's all text. It just keeps on going. Like if I'm to actually look into the data set,
It's huge.
so like this is one
It's-
session.
So I see it's like upward of
It's
800,000
like it just
more than a million.
800.
I would say million, more than million items, lines of code, right? Text. Yeah.
Yeah, and it's split up into 500 different samples where it'll each ask a question on one of them, but there's still like thousands of lines it has to search through.
Yeah.
It's a pretty difficult, complex data set.
And to mention the resources used, we put all of that into our prod public Moorcheh instance. And I saw you put in like upward a million items uploaded
Yeah,
into
I mean,
the
I can show the back end.
yeah. So back in Moorcheh, and this is not this is just our common deployment of Moorcheh. It's not even a special deployment, right? We just use the publicly available deployment, which is a one deployment on US East to get things running for the test. And you have created upward of 400, 500 different namespaces
Yeah,
for these. And there's no limit basically on how many namespaces, and each of them are another 500, 400 items in them. So that's the 2.5 million. No, am I correct? No.
250,000.
250,000 items just for this experiment, right?
Yeah, it's a really big experiment.
Okay. Now back to the now. Let's. Do we have any questions here in the from the team? Tara,
No, good. So
okay.
Yeah, okay. Yeah, so I have been working on a blog. So
I think Hit has a question.
Oh,
You raised your hand.
no, good. So fine, clear. He like answered it right after that.
Okay.
okay.
Yeah.
So
Yeah,
now to the interesting part of our conclusion. So just to give go ahead. I would give my you just
yeah.
tell
Yes.
finding.
Yeah, so we started going into research or like getting into this, like how exactly do other competitors, design their memory systems, and like how should that influence how we do it? And so we looked through and we saw all of them use complex knowledge graphs. So like here's like an example of like one this is vectorized hindsight, and they have a complex setup. They use link construction, like entity links. On top of this, they use semantic search. They use temporal links, semantic links. a lot going on, multiple queries. Yeah, and we saw this was consistent between like lots of competitors. They would also start to use knowledge graphs, and we thought to sort of take a step back a bit and like, do we really need to use knowledge graphs? And we're sort of new into the field, so we're wondering if it's necessary. So we started off and we used basic RAG just to see where it sort of stands with everyone else. And it kind of goes against what has been said before.
Okay.
Like this is
So, so I have an interjection here. Our basic RAG is actually a lot more advanced than anything they think of RAG, because we're using like information theoretic, patent pending, Moorcheh backend, which is highly optimized and highly accurate, and uses information theoretic information. So our basic RAG is already a very, very high performing RAG system that competes with a lot of the graphs builders. But continue, yeah.
Yeah. So like,
So
I mean,
Majid, you're
this,
saying, sorry, so Majid, you're saying that the reason that they pushed for the graph is because they didn't have the efficient RAG
That's
or
what
optimized.
that's our hypothesis. We think that they are doing RAG wrong. That's yeah. This is a good example. This guy
yeah,
from
I mean,
Zep.
this is like a year ago. I mean, I think this they still have this sentiment, or like they're using an example here, or like why they think RAG fails, and this is sort of the example they give, in that because they ask about sneakers, RAG will get the top chunk, which will mention that they love Adidas sneakers, but it will not realize that about the conflicts that are lower down because it doesn't tag sneakers. But this is not really an exhaustive case. Like
Yeah.
MUMLA would be able to resolve this easily.
Yeah. MUMLA actually handles this very easily. This kind of questions.
So the reason so these guys all are using like HNSW and cosine similarity for their RAGs, right? When it comes to optimization, so all approximation, ANN. So probably that's why they're getting. Well, we are using completely disruptive technology.
I would say the main difference between their RAG and Moorcheh RAG is that they're using approximate nearest neighbor, which is bound to miss some of the important ones. But Moorcheh does a full scan every time you do the RAG. You get a full scan. So if there is a needle in the haystack, Moorcheh wouldn't miss it. But other than that, is just also the score, the confidence score, and relevance score that helps you basically have a built-in re-ranker, a very powerful re-ranker, which combined together outperforms a lot of the existing methods. Yeah, please keep going.
Yeah, so I can talk about a lot of the findings I found while doing all of these tests. So we're going against the status quo and we're testing if RAG works. So one thing I found is about the number of chunks you return, or I guess it's sort of an understanding that perhaps if you increase the number of chunks you return, like this might be the chunk number 1, this might be chunk number 5, this might be like chunk number 20 or something, just as an example. And if you retrieve too many chunks, the assumption is that you'll start to get the model to hallucinate, or there'll be so much junk in there, irrelevant junk in the chunks, that it won't be able to sort of reason a solution. But as I was doing testing, I found that to not really be true, and that large language models of today can do like very, very strong, it has strong reasoning abilities, and you can retrieve a lot of chunks. And as long as you don't retrieve like the full context, there is like a balance. You can retrieve a lot of chunks. As long as a few of them have the information that you need, then it can provide like a strong answer. And I can see this in my tests that as I increase the number of chunks to 40 from 10, I get like like a major increase in my accuracy scores.
Mhm.
And then I kept pushing it. So I pushed that to 100 chunks. So
Mhm.
like in 100 chunks, maybe like 5 to 10 of them are relevant,
Mhm.
but I still see actually increases, like big increases in accuracy. And so the large language models of today are like very tolerant to receiving large amounts of chunks. And
Mhm.
like with our information theory,
Mhm.
semantic search, we're able to get the right chunks and that the large language models can sort of answer them correctly.
Again, yeah, I just want to say here we have some built-in functionality in Moorcheh. It's called kiosk mode, where you set a threshold and you don't really provide 100 chunks all the time. You just cut them at the relevance level. So there could be at some point, there could be only 20, it could be 30, there could be only 1, there could be 10. That's the variable, but that's decided by the built-in re-ranker method in the Moorcheh, which brings a cutoff threshold for you automatically. So
Yeah,
the point is that you're not necessarily providing all the 100 chunks all the time. It's just that you give it more room to expand and contract depending on how many relevant points of data there is, which could vary a lot. And you cannot put an exact number on it, but you give it the expansion up to 100 and then let it automatically set the threshold where to cut off.
yeah. So like we're giving back like a variable number of chunks. Like most of the time it will not give back this much, but like
Mhm.
maybe for some edge cases, maybe the question is like really hard and it needs to really stretch its search history.
Excellent. Yeah.
And so I actually looked into, so we got our sort of final results. We tried to do a accurate comparison using the same models, using the same prompts.
Mhm.
And at the very end, we got our exact scores, which is about 90% accuracy on the Long-Mem dataset, and then an 87% accuracy on the Locomo dataset. And we can, I looked through as many competitors as possible to see how those numbers compare. And it does like very surprisingly well. So I
Yeah,
mean,
very cool.
yeah, so like higher than super memory, mem0, zep, and like we're not the best. We're not expecting to be the best. We're just using a basic reg.
Yeah.
But
And this is our starting point where we haven't done anything. We just put it into Moorcheh and ask questions, right? And use the answer endpoint to see what we get. And we already starting pretty high up.
yeah,
And hindsight is doing a ton of preparation for the memory. And we're the only one that is achieving this kind of level of um, accuracy by doing traditional RAG system. Yeah.
yeah. I mean, if you look into sort of, because like when the initial problem we're almost trying to solve is that you're trying to not necessarily get the highest accuracy possible, but you're trying to get a memory system that is strong, it's consistent, it works, and doesn't like incur a lot of token usage. Because if you wanted to have a the problem itself we're trying to solve is that we don't like overload the context with so many tokens. So
Exactly. And the biggest point is that during the ingestion of all these memories, how many tokens did we consume?
yeah, so
Zero.
just like
Zero, basically.
Yeah, we are just simply implementing the chunk that we have and just sending it to the backend.
Yeah. And we can add one more layer of advanced functionality that is already built in Moorcheh, and that's we can create summaries for a collection of sessions and memories. And that would add another coverage of higher context architecture to the Moorcheh. But I'm jumping ahead. Maybe you just keep your own pace.
yeah, so I just want to I guess show an example of how some other agentic AIs sort of design their architecture. But This is sort of a concept idea of where you submit a query and then you get a bunch of chunks, and then now that you've got a bunch of chunks, you have an idea of what information you have and what you're missing, and then you redesign your query, and then you ask again, and then you get a bunch of chunks. So there are some agentic AIs that use this strategy, and it does work well. Like, okay, it does provide better results and get you higher accuracy, but the amount of tokens and like latency you incur by doing this is like very, very large.
Yeah,
And
you're kind of brute forcing it through the power of relying on the LLM to do the work for you. If it's not getting it, just saying, okay, LLM, please try again. Try to answer my question.
yeah, I mean, not all of them use it, but in order to somehow like get higher and higher scores, they're more reliant on using like more brute force methods, using more tokens, using like stronger architectures. So like we could get like higher scores if we like wanted to brute force. Maybe we want to use like more top K. Maybe we want to develop session summaries and like more sessions, but it's not the point to, I guess, get as high accuracy as possible. The point is that we've used a very basic, low latency, low token use case, and we've already beaten like most of the memory architectures. That it sort of proves that you don't really need all of this. Like all of this memory knowledge graphs aren't necessary. Like there is a use case where maybe you are trying to squeeze out the last few percentage points of accuracy, but for most developers, what they care about is something that's reliable and doesn't cost an arm and a leg.
Yeah, exactly. So the example I'm thinking about is, let's say, you have the information within your context. The issue is that do you want to spend, and you know that the LLMs are capable of extracting it somehow if you help them organize it and squeeze the relevance. But do you want to spend a ton of intelligence at the beginning during the ingestion to tag everything, to create entities, to create, distill all the relations, and then put it into memory, potentially hoping that at the time of retrieval, you would get higher quality of retrieval? Or you want to just have, and that's the approach we have, you want to have the entire context just ingested efficiently and put into a very well-performing, well-lubricated and optimized semantic system. And then at the time of retrieval, you use the highest intelligence to get the same quality. The difference is that the first method, you will have to spend a ton of tokens at every level of ingestion, and also you will have to spend tokens at the time of retrieval. But with our method, you don't spend any tokens at the beginning. You only rely on the intelligence once at the time of retrieval, and you get the same quality.
Yeah, like the major thing is that most like high-performing agentic memory stores rely on using knowledge graphs. So like I've made like a little chart here showing like which competitors actually maintain graphs, and maintaining knowledge graphs is very expensive. And because like during ingestion, every time you ingest, you have to build upon that graph, resolve conflicts, develop entity connections, resolve temporal conflicts. There's like a lot to maintain. But when you're using just a semantic vector store, there is no token cost incurred through ingestion. So it's like it is like a major saving and a major difference.
Whenever possible, we do that too. Like MUMLA by default tags the memories in a working session. If you work with MUMLA, tags the memories, adds the confidence level, adds the provenance, tells who said that. So those are in our metadata, which is searchable through specialized keyword searches, which further enhances your quality of the answer and retrieval. But here we are just comparing apple to apple, given the benchmarks, doing method A, how others do it, and just how we handle the benchmarks. Okay. Yeah. Keep going.
So I'll just show like a quick example of my own setup. So right now I am running my local MUMLA server. So I have like a lot of the setup done already. And like to see how to set up, there's like another video that we have where Het Kumar explains how to set it up and all of its features. But right now I'm using a local MUMLA server with a Moorcheh API key. And then I'm making API calls to this server, which calls the Moorcheh backend. So there it's running. And I just want to emphasize my setup. My setup is very, very basic. So I have my answer endpoint. So in order to call the answer endpoint, what I do, like this is not a long function. I am searching the memory. So this is just retrieving the chunks. I have the memories. I make my prompt. I have a prompt header. In order to make the prompt, I combine the prompt header with my context, and then I add the question. And then I just call the model.
Yeah.
So like it's a very basic RAG setup. This is the entire retrieval setup.
Exactly. Yeah.
And then I make this call. I have all this set up. I load the samples. So right now I'm just gonna ask a question. So the question is, how many model kits have I worked on or bought? This is part of the Long-Mem data set. So it has to find, or the idea is that in the ground truth, it has to find 5 model kits. So it has to find the specific models which are mentioned sparsely throughout all of the sessions.
So this is a real world example of multiple session question, one of the most difficult categories of questions across a conversation that was spanning through multiple sessions. Each session could be hundreds of dialogues, and it just haphazardly mentioned a few models. And now looking at the context, it's exactly pinpointing when and where, in which conversation each model was mentioned.
Yeah, so like it's able to find the chunk where it's mentioned very sparsely, and then it like has overlying context. The LLM is strong enough to know when this all happens. There's like associated timestamps which we have with MUMLA, so it knows when they got it, and it gets the question right.
Perfect.
Yeah, and you can sort of see the kinds of questions it asks. So like, and like the kind of solutions it's expecting, like how many days did I spend camping? And there's a breakdown. So like it has to find, it went 5 days on a camping trip and then 3 days on another camping trip, and it has to add them up into 8. Like how many weeks, how many plants did you acquire, the total money spent. So it has to add up all the expenses that are accumulated. So it adds like $120, adds up $25, adds up $40, and it adds them up to $185.
Yeah, and this is just, we're talking about the most difficult section, but do you have the breakdown of the score on different categories? Because there was a few categories that Moorcheh was getting 100% accuracy, like for the single session question. Basically saying that if you do the RAG correctly and properly, there's nothing will be missed. And if your answer is in the category, you wouldn't be missing it using the method.
Yeah,
so
I have a small report, but like you can see the distribution here.
Yeah, so for single session accuracy was 100% for the questions.
So it got every single question right.
Everything, and I don't think any other of those were able to hit 100% on that category.
Yeah.
Okay, yeah. So no one hits the single assistant at 100%, and also on the single precision preference,
Yeah.
the top one.
So these are like highest across all models. Everything I could
So
find.
there's
did the best.
super memory there.
Yeah,
Yeah.
super memory also hit 100%.
Just to
For
correct.
single session
Yeah.
preference, no, we hit the highest.
We hit the highest, and also on single session assistant, we hit 100% category. Okay, great. What's the conclusion now? I would assume, right? Are we towards the the trade-off?
Yeah.
I think we talked about latency.
Yeah, latency.
Let's talk about latency here.
But yeah, like there's so many with our setup, the factors that introduce latency, like the majority of the latency is just calling the model once. But all we do, like the majority of the latency is just like calling Gemini.
Mm-hmm.
But when you have like a knowledge graph, there's like much more that goes on. You have to like query the graph. You have to query the graph and get like certain entities out of it. You have to find their connections, and then you use those entities to like write another query. And then sometimes even if that query doesn't get everything, they'll might ask another query, and then it introduces more and more latency.
Yeah, and Moorcheh has built-in search engine that is within 20-30 millisecond response time just for getting the relevant chunks and doing the ranking,
Re-ranking.
and also threshold. Then the intelligence, you have two options. You here, for the sake of the experiment, to be on the exact level as others, we called Gemini, because most of them compared to Gemini, and we wanted to be apple to apple, because intelligence of the LLM at the end matters. Right? But Moorcheh has a built-in access to Bedrock models if you are on AWS, or if you deploy it on GCP, has internal access to LLM models.
Yeah.
And if you use the internal answer endpoint, it could be faster even, right? Because you eliminate one back and forth communication within that. You just get the answer in one shot from the MUMLA answer endpoint, right?
Yeah, there's like so many optimizations that we have. Like we use Gemini to be sort of on a similar level, or like comparing apples to apples with other benchmarks. But because we have everything locally, or everything in Moorcheh, we have our own re-ranker. There's like, if you have like a memory system, they have to call a third-party re-ranker. They have to call an API separately. You have to have your own like Gemini API key or OpenAI API key. But as long as you have your Moorcheh API key, Moorcheh MUMLA will do everything for you.
That's it. And that is not just the convenience, it's a major security advantage, right? Because you're not doing API calls to like 10 different places. You have an enclosed system. Yes, Neil has a question.
No, I just want to explain like just want to add more to the what Rasa just mentioned. That he mentioned that, okay, if you are using the other RAG platform, that you could probably need a drag or the re-ranker from the outside, and I think we measure when we are trying to optimize for the price, and then we found out that, okay, re-ranker cost is so significant. That's why there's kind of try to avoid the going with a RAG in place of for the memory. So if you have this like a advanced RAG, then you probably won't need that like a go for the another like a replacement for the RAG. Since we have the built-in re-ranker, so you won't need that. So it not only just avoid the latency, but also avoids the huge cost for the re-ranker. And that also like reduce the security effect, because you are not going to the third party. What you do is in the Moorcheh, you get the model from the Amazon only, you do the search in the Moorcheh only, so you just enclose in the whole private system, so you are not making the call outside of your VPC.
Exactly.
Yeah.
And yeah, to your point, Neil, we mentioned it a couple of times, but
Yeah.
I think RAG is getting a bad rap
Mm.
because most people are doing it in a very inefficient way.
Yeah.
As I mentioned, so they take a vector database from somewhere and then take some embedding. Let's say they just some embedding that they take vectors, and then they have to use another. They bring in a re-ranker if they want the quality, of course.
Yeah. Yeah.
And they suddenly add up the overhead of all these components put together, and then they have to call LLMs and then build the graph, and it's such a like a incoherent
Yeah.
system that is not really tuned or optimized to work together.
Yeah.
And what we did is we eliminate all of that. You have one strong information theoretic engine that takes care of it locally and on your own private cloud. And we are happy that we did that because now it turns out that it's going to help you with AI memory.
Yeah.
If you don't have a very good RAG, you will be chasing like all kinds of different graphs and vectors and combination of keyword search and thing, but it still wouldn't give you this solid quality of a well-designed RAG system. Yeah.
And yeah, it's just like a great point, I would say, because since we are a fully serverless, so it completely reduced the overhead, like for the developer, for the DevOps, it just reduced the whole thing. You do not need to manage the cluster or spin up the other cluster when there is a spike. You can just reduce scale down to the zero. So that's a great advantage that the Moorcheh have. And you just simply focus on how to build the RAG, and you can just grab the API key, build the RAG in literal 1 or 2 minutes. So
Yeah.
it's super easy.
And our infrastructure cost for that is that when you're not using it, it costs you exactly zero.
Zero, yeah.
And then uploading all of this data and doing a lot of those RAG, it costed us only I would say the highest cost we paid was the token.
Yeah, that's all.
Because we own the entire architecture, it's not costing us anything because it's stateless, serverless, very efficient. Yeah.
Yeah.
Okay. I think we're up to the time. We just have a few more minutes. So Rasa, is there anything else you want?
I guess there is like something I want to say, or I guess it's my sort of like opinion that in the space of agentic AI, that RAG was sort of written off early. And you can see that in the way that other products have gone towards building more and more complex graphs. But I think that RAG is not supposed to be written off that early because like in itself is such a strong tool, and that maybe back then they didn't have as strong LLMs and it was failing to do certain operations, understand temporal awareness. And that resulted, their solution to that is to manually build the memory system themselves. So like manually build entities, build entity relationships, and then build knowledge graphs in attempt to cover up for what their semantic system couldn't do. But now in this time now, we can see that the semantic systems do just as well as these knowledge graphs. And so the RAG was sort of, I think, written off a bit early in terms of performance and accuracy.
Yeah. And this is the very good point. So I remember when the first graph RAG came in, it was a patent by Microsoft, and Microsoft was the first to release that graph. And I was one of the early adopters. I was so excited. I started building graphs, and I realized, oh, this is all prompts. Like this is builds the prompts. Like it takes all the chunks, it does the same thing. This builds the chunks, and then asks LLM, please give me entities and relations, and then just saves it. It's basically, it's. You mentioned manually, but I would say by manually you probably meant giving to LLMs to do it in a kludgy way. not a systematic way, but we have this systematic way of building knowledge, still considered traditional vector based. However, because of our information theoretic score, which is a universal relevance score, we have some ways of building graphs that are actually very efficient and very meaningful, but we haven't done it yet. So this is our starting point. We start pretty high up, but we have plans for future development that would actually blow off the roof on these benchmarks. Yeah, on that note, and I want to thank you very much, Rasa, for this excellent. So,
Yeah.
and tell us where would this be available, and how can people find out more about your code, your research?
Yeah, so MUMLA evaluation, this is private right now, but eventually it'll be a public repository. You'll be able to see the results and everything. You'll be able to see more specifically what it gets right, what it gets wrong. You can run the tests yourself. So there's like running the benchmarks. You have the Moorcheh API key and the Gemini API key, but the Gemini API key is just to set up parity with the other products. If there doesn't need to be a Gemini API key, and then you just need to ingest the data and then run the evaluation. So you have the system set up for other people to test the results independently if you want to validate the results yourself.
Excellent. Yeah.
Yeah.
Very good. Thank you so much, everyone that paid attention. If you want to test MUMLA and you want to get early access, please reach out to us, connect to us through our Discord channel, or share our videos and comment on the video, and we'll be happy to connect with you and collaborate on this. MUMLA is going to be open source. It's going to help a lot of developers or early adopters of AI to benefit from a long-term, persistent, accurate memory that does not bankrupt them. Very efficient in terms of infrastructure. Yeah, so very excited. And thanks again to Rasa, Neil, and Head for the great work. And Tara had to leave. But yeah, keep in touch, and looking forward to the next videos.
See you.
Yeah.
Bye.
Bye-bye.
Bye bye.